Hello and welcome to Legal Knowledge. My guest tonight is Keith Dinas. He is an associate professor of physics and mathematics at the University of Arizona. Tonight's topic is theoretical physics rules the world, and he is definitely pretty good at that. Sort of
ruling the world, yes.
Yeah, ruling the world and theoretical physics.
Right.
The same thing we do every night. This is part one of a part two episode. Two-parter for the season finale. In 2 weeks, we'll be doing the implications of theoretical physics ruling the world. And then it's on to season 3. Unfortunately, we're not going to be showing our shows because the lottery ended up giving me 30-minute shows. They will now be airing well, it'll be March the 12th, Wednesdays, will be the live shows. At 9 p.m. again, and then on Friday at 11 will be the replays. So we won't be on Saturdays at all, and we'll also only be a half hour, which is well. But nonetheless, there is a season 3, so stay tuned. We'll have to adapt the format just a little bit, but it'll still be live call-in. We will be taking your calls later in the show. The phone numbers are on the screen if you're watching live. You can suggest your topics at illegalknowledge.com for season 3. Well, we want to say hi to Kyler.
Yes, hello, Kyler.
Hi, Kyler. Hi, call in, okay? So anyway, tonight's topic being theoretical physics rules the world. It's interesting because usually the show, obviously, is on things of the government and things that we shouldn't be, supposedly shouldn't know and everything like that, but this is actually a unique topic, and because everyone should know this, and it's not only should be, but it's not a thing that the government doesn't want you to know. In fact,
no, this is something the government really wants you to know. Theoretical physics and physics in general is research in these areas is paid for by us, the taxpayers, through the government. This is exactly how it happens. The government sponsors all of the research that goes on, much of the research that goes on in the United States through things like the National Science Foundation, the Department of Energy, and these people give out research grants to professors at their universities, do research, hire graduate students, such as the U of A. In fact, the U of A is one of the top universities, is the #1 university in the United States in terms of research money from the government coming in for the physical sciences. And so that's here in Tucson.
Yeah,
and
awesome.
As part of giving out these grants, one of the requirements that a grant proposal, somebody who writes a grant proposal has to be able to show is how they're going to incorporate the results of their research to disseminate them to the public. So this is exactly the kind of show that the government wants scientists to be doing. So this is not just illegal knowledge, it's legal, it's super legal, they really want you to do it.
All right, well, and then so it being, your specialty is?
My specialty is theoretical high-energy physics. My subspecialty within there is string theory and ideas for physics at the cutting edge of what we call the standard model and beyond the standard model, which describes physics of very small things.
And so that's basically, we're discerning what the building blocks of the universe
What the building blocks of matter are that build everything we know from the fundamental constituents, and also what are the laws that govern how those constituents interact. These are the basic things. What are the nouns and what are the verbs? How do they all work together?
Yeah, and we're not only talking particles, we're talking actual space-time itself, the dimension.
Right. That's right. That's part of the space in which this all happens.
But they're insofar as that they're interlinked.
That's right. It's all part of the same game.
Yeah, because people look at time and space. Well, way back when I was curious about all this, because I went to college and took physics and all that, and I wasn't anywhere near where I left college and I didn't know what time was, and I'm like, what?
What is time?
Yeah, I'm like, well, what is? Because when you look at a clock and it goes around. That's movement. That's not time.
Movement is one way you detect time passing.
Right,
Things
but
change
it's not
as
in
a
fact
function of time.
And I was like, well, what is time?
What is space?
What is and this
the same question, really.
So I went and read a whole bunch, but I still, it's I don't know anything really compared to what's going on right now.
At the ultimate level, scientists still don't know everything.
Yeah.
That's why we do research. That's what we're engaged in. That's sort of the excitement that drives the field.
But in terms of the answer to the question, it's a dimension, time.
Time is considered to be one dimension, just like length and width and height.
Yeah, or
exactly.
3 dimensions.
That's right.
And,
so we don't talk about a three-dimensional world. We talk about a four-dimensional world, exactly, including time.
And time.
Right.
Yeah. And so, first of all, I mean, to do like a real easy little thing, I mean, we basically think that there was a Big Bang and that, what is it that we're in is, the universe right now is that we're in a four-dimensional space-time.
Well, we think it's four-dimensional, maybe not. Yeah.
Rapidly expanding, slowing down.
Well, we believe more or less that the universe started out in some sort of hot, very dense phase, maybe perhaps the result of some sort of Big Bang explosion. It has been expanding ever since. It's becoming cooler, less dense, and we are in this state now. And this is observable partly because we're able to look at distant objects, which means light took a long time to get here from them. That means we're looking at the way things were in the past.
When the light was sent.
Exactly, when the light was sent. So we're learning about how things were in the past by looking out at distant objects. And so the evidence is that we are expanding, definitely. In fact, the rate of expansion may even be increasing. This is a new surprise for the past decade. This is something called dark energy.
Yeah, oh, okay.
And so this is what we believe now is the current state of the universe. We're expanding and even a little bit accelerating in our rate of expansion. So
that might mean that we'd cool even more rapidly.
Yeah, right, exactly. So it's a kind of very interesting time in cosmology because this explains how we got here and where we might eventually be heading in terms of the ultimate fate of the universe.
They're putting up, or not putting up, but they have that new space one, the space-based telescope.
Right.
And that's supposed to see back.
Hubble is a space-based telescope,
Hubble
and
it's
shown many
years.
Or
something?
What?
Is it strange?
I'm not sure exactly how far back in time they can see objects, but it's been able to see an amazing amount of things that were never seen before, and not only that, but with a clarity that's never been able to be seen before. And the more you're able to resolve objects, the more you can learn about them. So it's really been an exciting time in cosmology, not just because of Hubble, but there's been many, many other experiments also that are part of understanding how the universe works.
And then they're building like these super large mirrors and with that on
here in Tucson is exactly where they do this.
In the optics.
That's right. That's right. There's a big facility called the Mirror Lab. It's right next to it's right under the stadium on the U of A campus, and that's where they build a lot of the mirrors for these telescopes.
And
so it's really exciting.
These are going. The new ones that they have planned for like 2014, 2016 are supposedly going back like 13 billion years. Which is long time. Really close to the Big Bang.
That's right. We believe the universe is about 14 billion years, something like that. So we're able to understand a lot of the time already.
Like 14 billion years ago, when the universe was like really, really small, the forces hadn't separated, and there's a thing called symmetry.
That's right. Well, they're separate things. We believe at the earliest times when things are very hot and there's a lot of energy around, that we're really in a very high energy phase when all of the different forces and particles, perhaps according to current theory, were merged essentially into one kind of grand force.
A unified force.
Exactly. A grand unified theory is the kind of theory we talk about. And at that very high energy scale, perhaps that was actually realized in nature. So
it was the normal state of things for a very brief period,
and as things cooled, basically those kinds of very nice big symmetries had to break. And I can describe what breaking is and what symmetry is if you'd like.
Yeah, go ahead. So because I think that people, I think people would be interested, and I think that,
Sure. Okay. Well, a symmetry, there are lots of different kinds of symmetries. You imagine, you look at the human face, and what's the same on the left is the same on the right. That's one kind of symmetry. Cylindrical symmetry, for example, if you have a cup like this, and it has a cylindrical symmetry, it's the same if you rotate the cup from any direction, it's the same.
It always looks the same.
That's right. Yeah. And we believe that the laws of physics have these kinds of symmetries, that they're the same, even if you change your perspective on how you look at the object.
But if you change your perspective in a different sense, I mean, is there something that's comparable to the cup?
Well, this is actually something called a rotational symmetry, and we do believe that there's a certain kind of isotropy, a certain rotational symmetry in the universe. There are other more abstract mathematical kinds of symmetries, but they all boil down to different extensions of this.
It looks the same.
Yeah, exactly. So they all refer to different ways in which you can look at the same object, and from a different perspective, and the physics, the image doesn't change; it's invariant. But the idea is that if you imagine that your world has a cylindrical symmetry, and now, so you imagine that, well, that means that your pen has to stay straight up, because to choose any particular direction would break that symmetry. It would single out one particular direction in space. And that's okay if the universe is very hot and lots of energy, but as you cool things down, it wants to find a lower energy state, and it goes plop, and that means now you've broken the symmetry. And so in the same way, the grand unified symmetries that might have existed in the early universe when things were very hot get broken as you break down.
And this happens as it cools,
as it cools, symmetries break, exactly.
So now, should we be in store for another breaking of symmetry? Like right now we have gravity, which was the first one to sort of break symmetry. Right?
Well, we believe right now that there are 4 fundamental forces. We believe that we know that there is the gravitational force. We know there's a force which I can basically call electromagnetism. We know that there's something called the weak nuclear force, and we know that there's something called the strong nuclear force. And all of these presumably were unified together, perhaps in the form of some sort of grand unified theory like a string theory. And then now we know that as we've gone down in energy in the present day world, we see these all as very different forces. And so since we understand everything up to the current energy scale, we don't believe that any further breakings will happen as the universe expands, but certainly we know that if we go higher and higher in energy and probe backwards, we hope to see evidence of these theories that say that everything unified.
And we can do that using the new the colliders and whatnot.
That's right.
And there's this new
colliders
thing coming on.
Exactly. The Large Hadron Collider is going to be the super energy collider machine that's out there. It's being built in Geneva, Switzerland, at the European Laboratory for Particle Physics. I used to work there, in fact. And it's a fascinating thing because experimentalists have been building this machine for 10 years, 15 years. It's a major project in high energy physics. This is going to be the first machine to really probe the next level of matter at the next smallest fundamental scale, the next highest energy.
In a scale, like compared to, say, Fermilab or CERN, like CERN is about here and Fermilab is here, and this is like...
This is way well, CERN is where the LHC is being built.
Right, but
so
I mean,
this
their
is CERN.
current little...
What they've had,
they have a little
they've had a collider already, the large... They've had one, but this is the one that they're building now. This is the Large Hadron Collider. This is going to make what Fermilab has done much more. This is much more powerful than Fermilab.
Like on a factor of
10,
I mean,
maybe.
10?
Which is a major thing.
Which is...
That's right.
And
definitely.
so in terms of like a time scale back to what type of energies?
Well, we're going to reach an energy scale in the tens of TeVs, teravolt energy scales. Tera electron volts. So this is really exciting. It has taken a history of particle physics of 50 years of successive experiments to get to this point. And this is a very special energy scale we've really been waiting to reach for a long time. Because
there's this elusive particle, right?
Right. Yeah. This is the energy scale at which we expect to uncover the answer to the fundamental mystery, where does mass come from? And what breaks two of these symmetries, the electromagnetic force from the weak nuclear force. This is called the electroweak scale of energies. It's been a big mystery, and there's a particle, a hypothetical particle, which is responsible in our theoretical models for explaining all this, called the Higgs particle, and we're hoping to actually be able to see this finally and study all of its properties at the Large Hadron Collider.
And that's when you have the little plates that have all the little streaks.
Right.
It's just one of those streaks, basically, is you're looking for something that goes in a behavior pattern.
Exactly. You're looking for, they have these big detectors, and so these colliders bring these particles against each other. There's a collision. There's a massive explosion. We record, experimentalists, I'm a theorist, but experimentalists do all this work. They record all the different decay products. They study these things. They look for the most interesting ones, and then they analyze them and find evidence that for some brief period of time, a Higgs particle was created. And we believe we know what the signals of that should look like, the signatures of that, and so that's how they make discoveries at colliders.
So that's pretty much what we know right now.
Well, that's what we're hoping to find out.
But I mean, just back from the Higgs particle, we pretty much know that what we're looking at is what that is. Well, I mean, there isn't really much theory. It's more experimental.
At this moment, theorists have said, this is what we expect. And then experimentalists, please do the important job of finding it.
Finding it, right.
Exactly.
And they have, though, right?
Well, so not the Higgs particle yet, but they have found many of the things. Right.
So we're pretty much on the right track.
Oh, absolutely. And I don't want to give the impression that it's always theorists predicting and experimentalists finding. Most of the big discoveries, experiments have found, and then theorists have said,
theorists have to go back and explain.
How did that happen? And then we have to go and figure out new theories to explain what the experimentalists find. Physics, like all of the sciences, is experimental. We can have a great theory. If an experiment doesn't find it or finds something else, that's it.
Then that's so much for that one.
That's right.
Go explain this now.
Right. That's why it's so exciting. For 10, 20, 30 years, we've had this this current understanding up to the current energy scale, called the Standard Model.
Yeah.
It's been our theory. It's been beautifully confirmed.
Explain that a little bit.
And people have been trying to extend the Standard Model to find out what might happen at even higher energy scales. Yeah. And we have lots and lots of ideas about it, conjectures, and we've been waiting for 10, 20, 30 years for an experiment that will be powerful enough, a collider, that will be able to actually tell which is right, which is wrong, who wins, who loses, and this is what's going to happen.
Basically what, like quarks and leptons?
Right, so the Standard Model explains what are the fundamental matter, building blocks of matter, and the fundamental rules, the forces by which they interact, at down to 10 to the minus 19 meters. So this is
super.
Billions and billions, yeah, exactly, very, very tiny.
Smaller than an electron.
Oh. Well, it's smaller than a nucleus of an atom. Yeah.
Okay, so it's not small.
Yeah, electrons we believe currently, we've never seen a size for an electron. So as far as we know, an electron can be infinitely small. But a nucleus inside an atom has a size. Yeah. And then if you look inside the nucleus, you would see that it's made of protons and neutrons.
But those
and then if you look inside protons and neutrons, it needs higher energy to see even smaller objects inside. We find that inside really everything is made of quarks. And now the question is, what might be a substructure beyond that? This is another thing the LHC, the Large Hadron Collider, will look for.
Now, there's a thing called there's a superstring theory, which are like assumedly like the basic fundamental. This is the be all and end all.
Right. Well, it's one conjectured idea, a very powerful
we're nowhere near that energy, right?
Well, we didn't believe we were for a long time.
Now, how close are we?
Well, until 1998, it was really believed that the energy scale you'd have to probe to get to actually discover strings would be, if we're now coming to 10 to the 12 EV. Let's say 1,000 GeV. Let's use GeV as our unit of energy. So we're now going to approach the region of about 1,000 or 10,000 GeVs. What we would really need is 10 to the 16 of those to find string theory. Something
so
way
we're
beyond
10 to the 3 with our super collider.
That's right. So we're at 10 to the 3 now, and we need to get to 10 to the 16, 10 to the 19, and we're never going to do that. So string theory was
a collider the size of from here to Jupiter. Or
yeah, exactly.
Like
something that went around a planet or went around the solar system. Exactly. So obviously that's not going to happen. But one of the major exciting developments that happened in string theory around 1998 was the realization that maybe the fundamental energy scale and fundamental size of strings is not that small. Maybe it's actually quite a bit bigger, and it could be, it turns out, as big as the LHC will find. So it is a possibility that the LHC itself might stumble on strings.
Groups of strings and things like that.
Yeah, but even fundamental strings.
Just actual strings.
It could be that the LHC will begin to probe actual stringy substructure.
So, and
we don't
that's
know.
Supposed to go online when? And like,
well, believe it or not, they're going to have first beam in a few months.
Yeah.
And they'll spend about a year or two understanding their detectors and making everything work. Because in order before you can ever claim you've discovered something, you've got to make sure that everything else you've understood. So it's going to be a lot of work, and they're all set to do this. And within 2 or 3 years, it's going to happen, and it's going to be a new golden age in particle physics.
So they're going to try it on a low energy level first.
Yeah, first they have
to
make
sure it reproduces the experiments.
That's right. The first thing you have to do is understand your background.
Yeah.
And today's background is yesterday's discovery. So first they have to rediscover the Standard Model that we already know about. Just make sure they're seeing everything correctly and understand their machine. And then the things that are beyond that, well, that's the new discovery.
And then
they're looking for that because they'll be at higher energies.
It'll be like a year or so.
Yeah, very soon. Very soon. This is the exciting time. 30 years we've been waiting for this moment. Here it is, 2008, and it's going to happen.
Or 2009, but
8, 9.
Yeah, somewhere in there.
After waiting 30 years,
who cares?
It's now. It's not some hypothetical thing we're hoping for 10 years from now. It's happening right now. So this is very exciting.
All right. So that's what we'll be able to investigate. That's really cool. So what will we not be able to find? What's out of our reach completely?
Well,
what don't we know, and
Well, there are lots of things that are anything. Oh, yeah. Well, there are many things we're hoping to find out, but the universe is a big, complicated place, and there are things we know. Well, I'm quoting Rumsfeld here. Yes.
Yeah.
Things we know. There are things we know that we don't know, and then there are things we don't know we don't know. The things we don't know, for example, might be the Higgs.
Okay.
We haven't found it yet, but we kind of understand what it might be. Exactly. If you look at what the whole universe is made of, it turns out that the universe, we believe, is about 70% of a thing called dark energy.
Yeah.
That's 70% of everything.
I hear all these different theories about what that is, and one of the worst places to hear weird theories is like Coast to Coast AM.
Not true. Go to any high energy physics conference, you'll hear weird theories.
Okay. You get even worse ones. But do we have any idea what that is? I mean, do we really know anything about what this is?
Ultimately, no.
Could it just be like dust clouds?
No, it's not matter in the normal sense. Not at all. Not at all. We know that it's either, it could be as something as sort of static as just an extra coefficient in an equation whose origins are completely mysterious.
So it could be just a math error.
Well, actually, it was originally discovered and called a blunder by Einstein himself.
Yeah.
He wrote down
the ether thing.
Yeah, right. He wrote down a set of equations, and he added this extra term, and then at the end, the motivation why he added that extra term in the equations went away, and he said, "Oh, that was my greatest blunder."
Right.
Well, it turns out that term is there, so his calling it a blunder was not a blunder.
Yeah. Okay.
And it's actually 70% of everything. Everything in the universe, 70% of it is this dark energy.
And
then there's...
And that doesn't mean that it's energy that's like, as opposed to light energy. Like, we're not talking like energy from a star or...
energy, we're just talking about energy. Now, energy can be represented in terms of lots of different kinds of objects. This is something whose nature is completely unknown to us.
Right. Okay, so it's dark in terms of we don't know what it is.
It's called dark energy because...
And it's not dark because of its nature of characteristic of versus light.
No, really that too.
It is.
Really that too. Because another part of the universe...
I'd like to clear this up for everybody, because I'm a little uncertain.
Well, let me get to dark matter, because dark matter is the other is about another 26% of the universe, 25% of the universe. And so that is, we believe it acts like matter, like ordinary particles, but it's dark in the sense of not really interacting with light. We do not see it in terms of light. We can feel its effect in terms of gravity. So we can tell something's there. It's very heavy. It warps the space-time around it. But if we look for it,
that could be like dust clouds.
That could be something that we do not see in terms of light.
Yeah.
If you shine light on a dust cloud, you'll see that.
You'll see the light.
So this is something that just does not interact with photons.
So it could be like black holes.
Yeah, but even that disturbs light.
That
distorts light. We're talking about something that doesn't interact with light at all.
But
just interacts gravitationally.
Yeah, okay.
Or at least weakly, very weakly in terms of anything, not interacting with light. Light is a very powerful, direct way of seeing something. And so this is something that would be completely dark. That's dark energy. And the rest of the observable universe, all the ordinary stuff, this is all about 4 or 5%.
4 or 5.
Yeah, of the total universe. That's it. So these are other things we know that we don't know.
Yeah.
But then there's always the possibility of the things we don't know. A complete surprise that the LHC or any other experiment might just one day say, hey, look, here's something you never anticipated, and this is the way it is, and we have to completely revise our theories. So there's the things we know we don't know, and then there's the things we just have no imagination about. And that's why experiment is so important, because it tells us about the things we don't even know we don't know.
So it could be something just completely weird and...
Absolutely. Absolutely.
Okay, so I wanted to talk about the dimensions and things like that. Do we know what the difference between, why there is a difference between space and time? Why there is, like, what the, I mean, obviously we're living in it, but what is that? You know, how do we have any clue as to why?
Not really. We know that we can describe the universe in terms of 3 spatial dimensions and 1 time dimension.
But we have no idea why it's
We have no ultimate idea why. We can describe the universe in terms of that. So we can write down theories which incorporate that knowledge. But to explain why it is this way, we really don't have any idea. In fact, this is something now people are beginning to maybe develop a new approach to thinking about. Maybe there are other universes which have different proportions between space dimensions and time dimensions. Maybe the number 4 for the total is not even the right number.
Yeah.
And maybe there are different numbers of universes where extra dimensions are large, and therefore we see them and we say, okay, that's a dimension. And then maybe there can be very small curled up ones we don't see and therefore we don't even know about. And then the question is, if we started with 10 dimensions, let's say, and 1 is time and 3 are spatial that are big, and 6 others are really curled up and small, well, why is it that 6 are small and 3 are large and like space, and 1 is large and like time? We don't really know. There are lots of theories that maybe explain dynamically how we could have evolved that way from the Big Bang, but really, this is a complete mystery. So this is one of many complete mysteries.
More of what we don't know.
More of what we don't know, exactly.
Yeah. There's, in superstring theory, there's an idea, you were saying 10, I've heard 26 various numbers.
That's right. You know, it's very interesting, the history of the number of dimensions people believed in.
Yeah.
Originally, we always knew about 3 spatial dimensions.
But this is math, basically.
No, this is physics. This is writing mathematical equations that describe the real world.
Yeah, exactly.
And as we learn more about the real world and the laws that govern it, we write down different equations to incorporate our increasing knowledge. And as we've done this, we've actually keep changing the number of dimensions we need. So originally it was 3.
Give me the history.
Three spatial dimensions, because that's Euclidean space. That's what we all know. And then Einstein came along and said, really, we should think of time.
In there, too.
Exactly. So that made it 4. Yeah. And then in the 1920s, 2 physicists, Kaluza and Klein, Theodore Kaluza and Oscar Klein, said, you know, there were only 2 forces known at the time. There was gravity and there was electromagnetism. And he said, you know, we could make them seem like one force, a unification, if we just change the number 4 to the number 5. So then he proposed 5 dimensions.
Okay.
And this idea of unification requiring extra dimensions persisted for a very long time. And it lasted even until what we were doing in the 1970s, which was called supergravity, which said 11 was the magic number for supergravity theories. Then supergravity theory sort of fell out of favor, and then string theory developed in the 1970s and 1980s. And there are different kinds of string theories. And the easiest string theory said 26.
Yeah.
So that became the number. And then when people developed a more sophisticated kind of string theory called superstrings, the number became 10. Yeah. And it stayed 10 until 1995, when Ed Witten, a physicist, a very famous string theorist at Princeton, discovered that actually hidden in the equations was an 11th that nobody had noticed before. Okay. So we're back to 11. Exactly. So stay tuned. We'll see what happens.
The Soviet Union?
I have no idea. 11. Is it 11? Okay. Well, then that's the explanation. There we go.
It's a negative land song. Do you want to take calls here soon, maybe?
Sure.
Do we have people calling? Maybe, sort of? Okay. Well, you can call in. We might be taking some calls soon. Okay, let's see. I saw in one magazine or another where they're doing, I know you don't really have this expertise, but that they managed, there's this thing called quantum entanglement, where you manage to have part of the universe jump to another part of the universe. Kind of like in Star Trek, there's the transporter. And they call it quantum entanglement. And they sort of got it to work with light, which is kind of weird, but I guess they passed light from one place and it jumped through some boundary into
there was an
experiment
which could be interpreted in that way. Yeah.
And okay, but what is
As you said, it's not my field of expertise, so I certainly don't want to pretend to explain it, but...
Do you do anything...
Well, physicists do believe, though...
How that would work in terms of... Do we know? It's another thing that we don't know.
Well, I think they're using known laws of physics to do this. There's nothing mysterious about it, but they're able to achieve a certain effect which looks like something jumped from here to there. Really, the laws of physics have something called locality. We really do believe that physics is mostly determined. If I want to know the physics at this point here in space-time, I know that the physics nearby affects it most strongly, and the physics further away affects it less, and even further away affects it even less. And so this is just a property of all the laws of physics that we know. Physics is local. You need to know what's happening nearby to know what's happening here. And that's really very important for the history of physics. If it had been that to do an experiment in my laboratory, you know, in anybody's laboratory at the University of Arizona, required knowing what the guy at Princeton was doing in his laboratory and the guy in New Mexico was doing in his, and what might be happening on the moon, and all that could affect my experiments, and I could never possibly deduce any interesting new ideas without knowing everything about the universe all at once. And that's not the way it works. We learn about this, then we learn about that, then we learn about that, because the laws of physics really only care about what's happening nearby. So the laws of physics are local. But that doesn't mean that there can't be these kind of quantum entanglements which seem to suggest some sort of non-locality. Yeah. But really, still, they're following the laws of physics. There's nothing here that's violating known physics.
So I'm thinking in time also.
Yeah. Also,
because obviously through time, the laws of physics sort of, you know, between
the analog of that, the analog of what you're saying for locality in space is causality in time.
Causality in time.
Something happens today because something happened yesterday, and that causes this. Exactly. So, now, the world isn't exactly causal. Quantum mechanics tells us that really, if I know today's situation completely, there's a certain probability for knowing what might happen tomorrow. And there are a variety of different possible answers for things that could happen. But still, I can predict exactly the probabilities of what will happen tomorrow based on knowledge today.
Uncertainty.
Exactly. So physics is still causal in a certain sense. It's deterministic. Exactly. It's predictive up to a point.
Insofar as that the laws of physics throughout time are relatively constant.
Well, we believe so.
Well, except for back at the Big Bang when there was unification.
That's right, right. Yeah. The energy scale, there's a different effective theory at a different energy scale, and that changes as the universe evolves. So
what's interesting, I was reading this book by Freeman Dyson, which was talking about, it was infinite in all directions, and it was talking about how looking at E equals mc squared, he said that that it was a conversion chart essentially between energy and mass.
And energy.
And it's an interesting way of looking at it in terms of, well, when you have this energy, you can convert it to this mass, and here's the conversion factor.
That's right.
Which is the speed of light squared.
That's right.
And he was saying that that's really interesting because you can look at things like Hawking's black hole theory with the surface area of the black hole being proportional to its entropy.
That's right.
So you can change
the surface area is proportional to entropy.
So area can change to entropy. And there's the
entropy of an object is related to its area. This is a big surprise.
Yeah, yeah.
This is a major surprise. In fact, this really says something profound about theories that involve gravity, like black holes. Yeah. Because normally entropy is what we call an extensive quantity. The more of a stuff you have, the more entropy you have. You double the amount of stuff you have, you double the amount of entropy that might be there if it's the same amount, if it's the same property.
Just quickly for people, what is entropy? Because people might not know what.
It's a measure of the disorder. How much disorder is there? So something very organized and neat has a lower entropy. The more randomly disturbed everything becomes, the more it's all floating around in a chaotic way. That's a higher entropy. So when you heat things up, usually there's more disorder. More entropy. But if you just double the system, you just have one thing that has so much entropy.
The cup, I mean, potential energy, I mean, that's more entropy. Things tend to go towards higher entropy.
Things go toward higher entropy. You always find that your cup of milk, all the milk is neatly in the cup. That's lower entropy. And then if it spills over and all the milk flows out all over the place and it drips all over, that's higher entropy. You notice very often cups of milk will spill, but you don't notice very often that the milk gathers and puts the cup up. Now, actually, there's no reason that can't happen. That doesn't violate most of the laws of physics. It only violates a law of physics that says that entropy should tend to increase.
Yeah.
Exactly. So entropy is extensive. It means you double. If I had two cups identical, twice as much entropy. So therefore, the more stuff you have, the more entropy there is. But the measure of how much stuff you have is how much volume. Because when you double the amount of stuff, you double the amount of volume. So we would have expected that entropy should scale with volume.
But it does not. And it actually goes with area.
Exactly. In the gravitational theory, it goes with area. So that means we do not understand something deep about how many degrees of freedom there are in theories that involve gravity. There's not really an explanation for this. String theory provides one potential explanation for this. So what is that? Yeah. But basically, still, it's a great mystery about gravitational physics.
In terms of that explanation, can you...
Right. Well, what is string theory? String theory is the hypothesis that if we could look inside those quarks and look inside those electrons and look inside all the other particles that mediate these forces, we would find that they're all really just different vibrational modes of a single fundamental string. So just like a guitar string. Yeah. And you can pluck it in one way and make an A, and you can pluck it another way and hit a different note, a B, and so
when you do that, you're creating vibration, which is energy, which is mass.
Yes, different vibrational modes. Yeah. But there may be different vibrational modes that give you the same amount of energy also. Okay. So there's a richness in different notes that you can have, and what we believe in string theory is that all the different particles we see, and all the different variety of all the different ingredients, photons and W and Z particles and quarks and leptons and all these different wonderful elementary particles that they are going to discover at the Large Hadron Collider might just be different notes of a fundamental string. In other words, particles are being music. It's really a very profound, interesting theory.
Something that's spoken of in terms of non-physics
senses. Right. That's right. In fact, the idea that sort of particles and musical notes actually comes from, I think, some ancient Hindu texts.
Yes, it does.
Absolutely.
Yes, yeah,
so this is an old idea, a very beautiful idea. Absolutely.
It's actually, we're sort of looking at this as a real possibility.
That's right.
And that's really the way.
That's
I
right.
mean, way back, 4,000 years ago, how would you explain that?
Right. Well,
would you explain it just like that, perhaps?
Well, the ancient Greeks themselves started this whole game and said, what is the universe made of? Is it earth, air, fire, water?
Right, elements.
They're searching for the ultimate reduction of the universe into its fundamental parts. And really, string theory is the epitome today of the reductionist philosophy in physics. Go even smaller, ask what are the building blocks of the building blocks, and you keep going. And so this is the idea. So high-energy physics is the inheritor of this reductionist philosophy in physics. It's not the only way we learn about physics. We're not learning about complexity, for example, when we study just the smaller and smaller objects. Another branch of physics asks, how do these different objects come together to produce diverse natural phenomena? That's a whole different thing. We know the fundamental laws, but that doesn't mean we understand everything about the universe. So there are different ways of probing new things, but high-energy physics is interested in this reductionist idea of probing smaller and smaller energy higher energy scales, which means smaller length scales, to find ultimate building blocks. That's what we do. Yeah. That's what we do.
I'm just looking at the calls over there. There
right.
are a couple.
Oh, the lights are blinking all over.
There are a couple. Call in if you'd like. If you can see the numbers on your screen, you can go ahead and call. If you can't see any numbers on your screen, we're not live, and you're watching on Wednesday. In case you wanted to know what day it was, it's Saturday, unless you don't see numbers, in which case it's Wednesday.
An issue of time.
Yes, there we go.
We're in Tucson, that's space, yes.
And if you just joined us, this is Legal Knowledge. We're talking with Keith Ardinas, who's an associate professor of physics and mathematics at the University of Arizona. And the show tonight is entitled Theoretical Physics Rules the World. It's a part 1 of 2. And we're going to be taking calls. If you all call in, I see a call right now.
It's yellow.
And yeah, that means she's on. We'll be taking calls here, so give us a call. We will have part 2 in 2 weeks, and let's. I think she just go ahead and no, maybe not. Okay, I hope she knows how to use them.
Yes. Building the large hadron
We're not going
collider
to get any calls. It's
maybe an easy thing compared to figuring out how to use this switchboard.
Yeah, let's just figure out physics rather than figuring out how to use it. All right. So all right, so what's new about anything right now?
Oh, there's lots of new ideas. Always, you go to a physics conference and it's a very exciting thing.
Obviously,
you hear
the
lots of new
LHC is
ideas.
new.
The LHC is new, but until that, theorists are going wild with lots of new ideas. So there are new, one idea that's really new is that extra dimensions that could exist. We've all believed in them for a long time, but we've always thought, well, yeah, 10, yeah, right, 6 or 7 extra beyond the 4 we know to reach a total of 10 or 11.
What are they anyway?
What is it? What that means is that at every point, you believe that in addition to length and width and height and time, that there's some extra curled up dimension in a direction perpendicular to those 3 simultaneously. So you can't imagine it.
Yeah, so it's not, obviously it's not part of space.
It's part of space.
Is it part of,
it's just not part of the big space we macroscopically can observe. Like exactly.
Yeah.
But what that does mean, though, is that we can hope to measure this, we can hope to discuss this, because if we have high enough energy, then that means that we are accelerating our particles so that they effectively have a little tiny wavelength, and we can hear echoes. So how would you know if you entered a big room and you didn't have any light? You could hear an echo of your voice and the sound of the room, and then you'd know, oh, I can map out just like sonar. I could map out the size of an extra small dimension, a compact dimension, by just listening to those echoes. So that's what we hope to do at the Large Hadron Collider.
Can we uncurl them?
Well, changing the space-time is a little different.
Thing about that.
No, I've never talked about uncurling them because that takes a lot of energy. You'd have to put a lot of mass into a place and a lot of energy to deform the space-time. That's how you deform space-time. Space-time curls up or responds to mass. So you need a lot of mass.
Right here.
Right.
The planet's actually travel in straight lines around curved space-time.
That's right. The sun is such a heavy object, it warps the space around it. The Earth is trying to just go along in a straight line like everything always does, just straight lines. But because the space is warped, it doesn't know any different, and it thinks it's in a straight line, but it's in an orbit. That's our understanding of how gravity works.
Same as the moon.
Exactly.
To the Earth,
exactly. But what we hope
satellites.
Exactly. What we hope to do, though, is hear these echoes off these extra dimensions, and the echoes will look like new particles. So instead of just detecting an electron in a collider, we'll look for a copy of the electron called the Kaluza-Klein echo, and the second echo, and the third, all the harmonics, and then we'll say, that's it. That means we've discovered an extra dimension. So this is something really exciting.
We
Past
actually
10
might
years,
be able to with a collider, discover extra dimensions.
That's one of the major things that people are hoping or thinking that the LHC will do.
Yeah.
And that's actually what I've been working on for the past 10 years, understanding how the colliders might be used to discover these things and exploring the theoretical possibilities if these things exist, these extra dimensions. So this has been a big, exciting area. There have been other developments in string theory. For example, we've always understood that gravity is a very different kind of force than the other forces like electromagnetism. Well, now we've understood that actually there may be ways in which they're related. So if I want to do a calculation and understand some property of a complicated gravitational system, maybe I can do instead a different calculation just in terms of electromagnetism kinds of forces, and I'll get the same answer. So this is a whole new possible way of understanding that how to do calculations in the theory and deduce that maybe these different theories are really the same. This is another exciting possibility. A third idea that has really taken on in the past 10 years and become a major thing has been the question of how many universes are there? How predictive are things?
So I have a question here about that, because if the universe is everything, right?
Yes.
Then how can we talk about other universes?
Well, then maybe the universe isn't
they relate
everything.
to this universe.
Maybe the universe
then
isn't
they're
everything.
part of this universe, right?
No, maybe our universe is just one of many possibilities. And maybe in a disconnected way, they're parallel universe. People have been talking about this in science fiction movies for years. But there's actually a way, a sensible way now, in which physicists have come to think that it's entirely possible that there exist such other universes on what we call different branes, membranes kinds of things. And it's possible that there are these different universes.
Okay, so if they affect our universe, then wouldn't they be part of our universe?
Well, in some sense, they're part of the complete universe.
Right, well, that's what I'm saying.
And so what we're understanding is that our observable universe, the one we can travel in and look through telescopes to study, might just be one of many universes.
Subsets within the universe.
Absolutely.
The actual big scale universe. Yeah.
And this is a very interesting point because, you know, in the history of physics, we've always asked what kinds of numbers, what kinds of quantities are we able to calculate? So, for example, early times, centuries ago, physicists tried to get explanations when we knew the different orbits of the different planets. They said, oh, are they in some special ratio? Is there a special way we can calculate the special numbers or properties or magical, mystical properties that say the Earth is this distance, the Moon, the Mars is that distance, Pluto is that distance, and so forth? Well, they didn't know about Pluto then. And Pluto's not a planet anymore, so we can't talk about it.
Something like that.
But anyway, these were the kinds of numbers people thought a theory should be able to explain. Nowadays, we don't even try to explain those numbers because those numbers we call environmental accidents. This solar system happened to develop this way, and those are the numbers. We really care about the true fundamental numbers, like the mass of the electron compared to the mass of this quark and the mass of that quark. That we think a fundamental theory should explain. That's not an environmental accident.
Yeah.
Well, now,
if it was an accident, then it would be different across the universe.
Right, but now that we think that there might be other universes, other self-consistent solutions, maybe they have different values for these fundamental constants of nature. Maybe those numbers, too, are like the radii of the planets, and we shouldn't ask about those. In other words, we're starting to wonder what kinds of questions really should we be asking. Maybe everything is ultimately a question of environment, how we happen to land in this particular universe versus another one. And maybe we're not sure what theories are supposed to be calculating after all. This has been a major development in the past few years. People are very anxious, very upset about it. People have been using what are called anthropic arguments, which means, you know, maybe just because we're here, the fact that we're here means that these are the numbers that had to be because otherwise we couldn't be here and support life. And then other physicists say, no, this is crazy. You can't use that kind of thinking. That's not predictive. That's not science.
Well, Hawking said that.
Exactly. And I was just at a conference about a year and a half ago in Huntington Beach in California, and they had a whole panel discussion at night, and there was, you know, angry debate between Nobel Prize winners at a panel like, you know, sitting at a table like this, and four people, and one person saying, yes, I believe in the anthropic principle, and the other one says, how can you believe that nonsense? You know, there's a whole audience of distinguished physicists all getting upset and angry. But this has now become a rather interesting topic just in the past 3 or 4 years. So this is one other area. So physics keeps moving forwards. It's very exciting.
Though, that every possible solution that could be a solution happened.
Could be. Each one is realized in a different way in a different part of the universe. For example, if our universe that happened to have the numbers that we're used to inflated more strongly, more rapidly than other parts because our numbers were different, then the observable universe would be dominated by the one we know. That doesn't mean there aren't sections that still represent these other possibilities. They just didn't inflate very big, and we inflated big, and so most of the universe is ours. We won the election, so to speak. But that doesn't mean it's the only possibility. So people are now becoming very aware of these other possibilities. So as I said, physics is really in a very exciting mode right now.
So I always sort of propose this sort of thing there, that time had already happened, that the universe as a whole, all dimensions of it, happened, and we're living through it.
We're living to observe the evolution of the geometry of the universe.
Do you think that that's a valid point?
Well, we know that.
Or do you think that there's some actual distinct property that, you know, there is no outside time? We're bound to live through it in sequence.
Well, I'm not sure quite what you mean, but we believe at the Big Bang that space-time is created, and now it evolves in a certain way following certain deterministic laws. So, for example, just as if I have a ball at the top of a hill and we know it's going to roll down the hill, it's changing, its speed is picking up, its potential energy is going down, it evolves. We believe that the universe is now on such a path, and it evolves according to certain laws.
Well, you see, because in space you can see the end of the path.
That's right.
And in time, well,
it depends. We don't know whether we live in a, well, we believe, we have various beliefs, but we don't know really whether time will go on forever like space goes on forever. Maybe it doesn't. Maybe there's a boundary to the universe. Maybe things wrap up and come back to itself. What is the large topology of the universe?
Like the surface of the Earth. Well, Niels Bohr said that it's like a torus, the implicate versus explicate.
There are many possibilities for what the geometry is, absolutely. But we don't know really what the geometry is. We're still learning. In fact, it's an interesting question. What is the topology of the universe? This is another thing that people hope to find evidence for.
Now, was that when we look and maybe do find other dimensions, and is that going to be able to help us?
Well, that would change everything, because now we would know that, well, we wouldn't know about what maybe is the edge of the universe if there is one, or what is the topology.
Or if it's like
but we'd know the whole dimensionality of it. But we'd know the dimensionality of it. So instead of asking the question, does this dimension end, does that dimension end, now we'd have to say, well, there are 6 more dimensions maybe. What do they do? What is their geometry? Is it the same here as it is here? Does it evolve and change?
Space moving through time is, and then you have space-time moving through these other dimensions, and so you end up with all kinds of,
Absolutely. So really, one interesting thing that's happening now this century is that the study of physics is often, in these areas of physics, becoming the study of geometries.
Let's try taking it.
Okay, so I'll push on.
Just press that one. Let's see what happens. Hello, you're on the air. Actually, just hit this one.
Okay.
That one, and then you're on the air. Welcome.
Hello. This is Oscar.
Hi.
I guess I have a 2 or 3 part question about that satellite that's going down.
Oh yeah.
If the Navy knocks it down and all the stuff that's going down and it does land on Earth, what's it going to do?
Well, it should burn up in the atmosphere. That's what they're doing. We're actually talking more about theoretical physics and things like that.
You guys are way ahead of me. You guys are way ahead of me, so I'm sorry.
They're supposed to hit it with a missile because it's really a 2-part thing. One, China just knocked down one of their weather satellites, so we're basically saying, oh, look, we're going to do the same thing. Look how good we are. We can do the same thing. Number 2, we don't want the technology to get into anybody else's hands. So we're going to blow it up.
Okay,
rather than,
okay, 10-4.
Yeah, right on. Thanks. Let's grab one more call. Thank you, sir. Welcome. You're on the air.
Hello?
Yes, you're on Illegal Knowledge.
I have a question.
Yes.
Isn't string theory just mathematical theology?
Great.
A lot of people argue about that. The reason they say that this could be the case is because it's not experimentally verifiable, because we don't have the technology to produce the experiments that would be needed to test it. But here's my answer to that. Since you asked, I'm glad to answer it on television. A theory is theology if it doesn't provide any way of being testable and doesn't give you any prediction that can actually be verifiable. However, string theory does make absolute predictions. The problem is that it's not at an energy scale that we can probe. So it's a failure of our technology to test it, not a failure of the theory to make predictions. String theory is a theory of physics because it makes predictions. Just like there were theories of physics that made predictions at energy scales that we could not have tested then, but now test, they're still physics. It's a theory of physics because it makes testable predictions. It's a failure of the technology to be able to actually reach those energy scales and test it.
All right, yeah, that's interesting. I think we're probably good for now because we're about 20 seconds left, so we're not going to take any more calls. But I'll tell you what, all of you who called in tonight, please do call in 2 weeks because part 2 of Theoretical Physics Rules the World will be happening on March 1st at 9 p.m. This is Michael and Keith for Legal Knowledge. Bye-bye, everybody.
Thank you.